Okay, the recording started. I'd like to welcome you all today. We have our great speaker, Necmiye Ozay, present her talk formal methods for cyber physical systems, state of the art and future challenges. Before give our virtual stage to Necmiye, I would like to talk about her biography. So she received her BS degree from Boğaziçi University in 2004, her MS degree from Pennsylvania State University, and PhD degree from Northeastern University in all electrical engineering. She was a postdoctoral researcher at the California Institute of Technology from 2010 to 2013, and I guess that was the time I first met Necmiye. It's been over 10 years now. Then after that, she joined the University of Michigan, and she's currently as an associate professor of electrical engineering, computer science, and robotics there. Her research interest is quite various. She's interested in hybrid dynamical systems, control optimization formal methods with applications in cyber physical systems, system identification, verification and validation, autonomy, and dynamic data analysis. Her papers received various awards, and her group has been very active. Nation that she herself received quite a lot of awards from DARPA, ONR, NSA, and also from IEEE Control Systems Society. So I'd like to thank you again for joining us today. And now, please go ahead with your talk. And I guess you are also a co-host, so you can share your screen.
Let me.
Okay, we can see it. Thanks.
Okay.
I
think we can get started. Thanks so much for the invitation. So it's my pleasure to be here today virtually and to speak to you. And I hope I will be able to visit in person at some point in the future. So today I'm going to talk about formal methods for cyber physical systems. And given this is a robotics audience, maybe you are not that much familiar with formal methods. I know Ebru is doing lots of fantastic work in this area, but I will try to give an overview of formal methods in general and what has been done in the past decade or so and where the field is going. And some implications on robotics and some implications in other fields as well. Here's a quick motivation slide. So these autonomous systems are all around us, from self-driving to medical applications to construction automation and agriculture. And in all these domains, we want to have end-to-end guarantees on safety and test completion so that we can deploy these machines with much more guarantees and more broadly in various parts of society. Formal methods came up in the software domain to give these guarantees, mostly safety guarantees, on the performance of software systems. And this is a Wikipedia definition. It's essentially a set of mathematically rigorous techniques for specification, verification, and design of software and hardware systems. It started purely in the software side, but in recent years, people started using these type of ideas in cyber physical systems and robotics as well. So I will go over some of the main questions people study in formal methods and how my group studied those questions and how we contributed to those questions. Then I will move on to some of the implications of these questions and how they motivated new research in my group. So the main question people study in formal methods is this question of verification. So you have this autonomous system. Here, I will use autonomous driving as the main application. You have this vehicle model, and you have this physics, and you have a model for this physics in general. And you have some decision-making or autonomy software. And if you want to do verification, you have both a model for your physics and you have a model for your software, or you have access to your software. And you have a specification on the system. So you want the system to accomplish a task, and you represent the specification in some mathematical formalism. And you try to come up with this algorithms called verification algorithms. And an ideal algorithm takes this white box system, which is plant plus software, and the specification, and it tries to produce a correctness proof. And the correctness proof in this context means when you close the loop with the software around this physical system, it's guaranteed to satisfy this specification if you can get a correctness proof. Or this algorithm can also give a counterexample, which will generate an initial condition and a set of environmental conditions under which you will see that the system, this closed loop system, will violate the specification. So this is a very powerful paradigm. And if you can do that, you get very strong guarantees, and you can deploy your system and put lots of trust in what the system will do in real life. But there are also lots of disadvantages of this paradigm. The first thing is that since this was originally developed for software, some of the verification tasks were easier. But if you have hybrid systems that combine physics with lots of lines of code, the verification tasks become computationally very hard. One of the main sources of hardness, I will argue, is that in typical autonomy systems, most of the complexity lies in the software part. Usually autonomy software, it includes millions of lines of code. It's hard to model. If you try to abstract it and write a model, use a model instead of the actual software, it's very hard. And it's also hard to scale because it's really complex. So here are some small examples. If you look at Mars Curiosity rover, it includes 5 million lines of code. If you look at the average modern high-end car, it's 100 million of lines of code. So it's really lots of complexity hidden in the software. So people started thinking about, okay, this is hard to scale. Can we do something slightly different? And one of the alternatives people thought about is the following. It's called correct by construction control synthesis. Here, instead of taking this plant model plus the autonomy software, you ignore the software because software is the part that introduces the complexity. And you ask an existential question. You ask, given this plant model, does there exist a software that I can close the loop around this plant model, such that with the software, I will guarantee that my system will satisfy the specification. Again, the output of the synthesis algorithms, if you can develop these algorithms, will be a software that makes decisions for your system, together with some correctness guarantee and a domain of validity that tells you under what conditions about the environment and about the initial conditions of system, this software will guarantee that your specification will be satisfied. Or this synthesis tool can also give you a proof of impossibility. And by a proof of impossibility, what I mean is that satisfying the specification is beyond the capabilities of your plan. So no matter how smart you are, or no matter how smart your algorithm is, you cannot find a software or controller such that you will satisfy the specification. And this proof of impossibility is also useful because that tells you either need to go back to your specifications and relax your specifications because your physical hardware is not capable enough to satisfy those specifications, or you go back to your hardware design and you try to improve your hardware design. Maybe you put better actuators, maybe you put better sensors, and you can rerun this synthesis algorithm with this improved model of your plan. Of course, this has some advantages and disadvantages as well. Again, if you can do that, you get very strong guarantees. It avoids the complexity induced by software. I am saying avoids, but it's kind of pushing the complexity from the input to the problem to the output. And it explains fundamental limits by producing these proofs of impossibility. On the other hand, there's no free lunch, so correct by construction synthesis is computationally even harder than verification. But you are a bit luckier because your input to this problem is smaller, so you can still solve some interesting problems. The other limitation here is that the type of specifications you can handle is limited, and specification correctness and completeness becomes very crucial if you are doing synthesis, because this algorithm don't understand what your intent is. They will just spit out a software or controller that will satisfy the specification. But if your specification is not correct or complete, you might have trouble. And I will give some interesting examples of that later in the talk. And the other disadvantage here is that if you go to a modern autonomous system these days, there are lots of like perception loops and learning components, and there's almost no synthesis approach that can synthesize perception or learning components for you. So having talked about this advantages and disadvantages, I want to tell you a few things that we did in my group using correct by construction control synthesis. We have worked on applications in automotive and aerospace domain, and I will tell you a little bit about what we did early in 2014-15 using correct by construction control synthesis for autonomous driving applications. And in particular, we looked into adaptive cruise control and lane keeping. And we developed new synthesis algorithms. We synthesized controllers for adaptive cruise control and lane keeping, and we deployed these synthesized controllers in the MCD test bed. So at Michigan, we have this vehicle test track that's called MCD, and we have some vehicles where you can put your control software and run some tests. And these are some of the runs of this vehicle with software synthesized by our own synthesis algorithm. So maybe this is a simple autonomous driving thing, but the interesting thing here is that these vehicles are driven by software generated by some other software. So you just input the specification, you input some model of the physical vehicle, and the algorithm generates some software, and you directly put that software into the car, and the car is driving itself. We also have this like digital twin type environments where we can put the same software first into the simulation environment and test a little bit in the simulation before deploying in the real world. So our group was one of the first groups who did this like end-to-end synthesis with hardware implementations in realistic scenarios, and we learned quite a bit by doing so. By the way, if you have any questions at any point, please feel free to interrupt and ask. So what did we learn from these early deployments? One of the things that we learned is that putting correct and automatically synthesized software on a car is feasible. We say this is correct by construction, but correct is in quotation marks. So there were failure cases. But since we have mathematical models for the physical plant and formal assumptions that are formalized in our specifications, it was very easy to detect the root causes of these failures. For example, one of the things that we realized is that there were this failure trace when we were running tests in MCD, and we realized there was a mismatch between what the car was doing and what our model was predicting the car should do. And we realized there was a very significant actuation delay between the steering command and the actual rotation of the wheels. Another thing that we realized is you can do synthesis, but sometimes it's very conservative because the policies that we synthesize, they are typically state feedback policies. So they look at the current state of the car and they try to make decisions. And this is, in a sense, trying to drive by making a hole underneath your car. Just look down and try to drive that way. But we don't drive, humans don't drive that way. We look ahead and we predict what's coming up. We predict how the road is rotating and we plan accordingly. So we realized there's some conservatism, but we could also understand what the sources of these conservatism is. And this motivated some future work. We started working on how to handle delays in these type of algorithms, how to handle predictions, and how to incorporate predictions into these synthesis algorithms. We looked into, given that there could be model mismatch, we looked into problems where we are learning the model in the loop, and we are still trying to synthesize a controller and give guarantees. So these are some of the problems that we studied. And with that, I will try to dig into this actuation delay problem a little bit, which I found a little bit interesting. And if you're a controls person, you should be a bit suspicious when I start talking about delays and when I tell you that these algorithms are not scalable, because whenever you have delays essentially increase your system dimension quite a bit. And we are talking about type of algorithms that don't scale well with system state. And we realize although system state dimension is increasing when you have delays, there is too much structure in how delays enter your actuation so that you can get around, if you are being smart with your computations a little bit, you can get around and mitigate this complexity the increase in the state dimension induces. So here I am going to get a little mathematical. So this is a system with some actuation delay. So this is a linear system subject to some disturbances. And my inputs that I apply at this time become effective tau d time steps later. And I can write this delay system equivalently as this augmented system, where I just concatenate a bunch of past inputs. And this is a regular system without delay, with input entering here. And I can try to apply my synthesis algorithms for this augmented system. And the type of synthesis algorithm that I am going to talk about here is an algorithm that generates invariant controllers or safety controllers. And the problem that we are trying to solve in this case is that we are given a safe set for these states to be in the context of driving. These safe states could be being inside the lane boundaries or distance to the vehicle in front of you. And if you have a safe set for this original system, you can generate similarly a safe set for this augmented system. So we are given this safe set and we want to find a subset of states of this augmented system such that whenever we start in the subset C, we can find a control input U such that in the next step, we are guaranteed to be in the subset C, no matter what the disturbance does. And the disturbance in this case captures road grade, the behavior of other vehicles, or road curvature. And ideally, we want to find the largest possible set C, and that will give you that will give us the largest possible safe control domain. There are methods for finding these safe controllers. So you might, one popular thing in recent years is control barrier functions, but the result that I will tell you is independent of the method that you use. So you can go ahead and try to apply those standard methods to augmented system, but this is computationally very hard. And the computations in most of the cases scale exponentially with the state dimension. But what we show is that given this augmented system, you can define a map. It's kind of a dimension reduction map T that predicts the future states, assuming you don't have any disturbance. And if you look at the dynamics of these predictions, the dynamics of the predictions, you can write them in closed form, and they are still a linear system. And the dynamics of this prediction is still in this low dimensional space. So if your original system is n-dimensional, the dynamics of this prediction is still n-dimensional. And you can go ahead and design your safe controller for this predicted state. And you can define a careful inverse of this map or pre-image of this map to lift the safe set that you compute back to this high dimensional space of the augmented system. And that lifting gives you a safe set and safety controller for the augmented system. And the interesting part is that if you find the maximal invariant set for this low dimensional system, you can recover the maximal invariant set for this high dimensional delayed system. And instead of solving a problem that's exponential in the dimension of this augmented system, you are solving a problem that's exponential only in n. And the result, the complexity is independent of the delay that you have. And what is the implication of this in experiments? This is the time it takes to compute these invariant sets as the delay size increases. And if you do the standard computation, try to compute that safe set in the high dimensional space, you see this exponential, roughly exponential blow up in the time it takes to compute. And if you do this trick, there's a very mild increase in the time. And the reason for this increase is there's some computation you need to do to define the inverse map. This is kind of interesting for me because like I do mostly theoretical and algorithmic work, and going and doing some experiments in real world motivated some new theory. And we ended up designing these type of controllers. We put them back into the vehicle, and we could also observe increased performance. So this is one thing to overcome these challenges with verification. The other alternative people studied to overcome the challenges with verification is falsification. So in falsification, you study a slightly different problem. You say, okay, I wouldn't use a model for the plant. I wouldn't use a model for the software. I will just take everything as black box. And if you do that, then you can have very complicated software. You can have perception modules. You can have learning modules. It's all fine because all you need for falsification is a black box you can query. And you have some specifications, and these falsification algorithms try to find counterexamples. So they are smart sampling algorithms that try to find counterexamples, initial conditions and environmental conditions for your system, such that the specification is violated. The advantage here is that you can handle arbitrarily complex plants. You can handle learning components, and from formal methods community, there are some tools that are developed within the academic community that are adopted by industry. So I know these tools are now used in automotive companies as Toyota and Ford. But the disadvantage is you have weaker conclusions, and there's no explanation of the counterexample. So they can give trivial counterexamples if you don't write down your assumptions carefully, and you don't have a sense of whether this counterexample is a limitation of the physics or a software bug. So again, this was interesting for us, and we started looking at this problem, and we thought, okay, there are problems where we can really model our physics, and falsification is totally ignoring the physics. Typically, if you have a model for the physics, can you do something better? And we came up with this paradigm for doing synthesis-guided falsification, where we will use our plant model, and instead of trying to analyze this entire closed-loop black box system, we will assume and we will utilize this plant model, and we will try to find the bugs in the control software itself. And again, we can get counterexamples using synthesis-guided falsification plus an explanation. And that explanation will tell us whether the counterexample is due to the limitation of the plant, or due to a bug in the software. And of course, it's inconclusive if it cannot find a counterexample. And the key insight here is that steering the search via the specification and some backward reachability using your plant model, and querying this unknown controller only at parts of your state space that are specification critical. So we developed this algorithm, and we were looking for applications. Then we came up with this startup, AI. I don't know if any one of you is familiar with this AI. So this is a startup started by, I keep forgetting the name of the guy. This was a hacker who first hacked the iPhone. But if you remember, when iPhones first came up, Apple claimed that they are not hackable. And there was this hacker who hacked the iPhone. Then he had lots of startup companies, and he has this company called AI as well. And the promise of AI is that they had this device that you can put to your windshield that has a camera in it. And if you have, they have like 40, 50 vehicle models. If you have one of these vehicles, they tell you how you can connect this device to the canvas of your vehicle. And they claim that with this device, your vehicle will get the autopilot properties of a Tesla, more or less. And they wanted to sell this thing, and National Highway Safety Agency, NHTSA in the USA said, no, we cannot let you just sell this to everyone and claim that they will have self-driving cars. So they found it very unsafe to let a startup owner to sell these type of devices. Then the guy said, okay, if you don't let me make money out of it, I will just make this thing open source. Then they put the entire code base to GitHub, and they also have like this open source hardware. They tell you how to build this thing yourself. And in the new version, you don't even need to build this device. You can just put your iPhone there, and they tell you how to connect this iPhone to the canvas of your vehicle. And they claim you can have self-driving capability. And if you search on YouTube, there are lots of people trying this on their own vehicles. And you can try, if you are brave, you can try it on your vehicle as well. So we took this software stack, and it has this adaptive cruise control lane keeping type functionality there as well. And we ran our synthesis guided falsification algorithm over it. It turns out that it's very safe. So for adaptive cruise control, we couldn't find any counterexamples. The only counterexample we could find, if you call it counterexample, we couldn't find any scenarios where we could make this crash because it was braking pretty conservatively, but they had an internal safety margin saying you shouldn't get close to the front vehicle more than 3 meters or so. And we found scenarios where it was sort of violating its own safety margin. For lane keeping, though, we found some cases where if it's a sharp turn, this lane keeping controller would take you out of the lane. Whereas with our synthesis guided falsification, we can devise supervisors and override this unsafe controller and make a safe decision from the same scenario. So we wrote this paper, we put the paper on archive. 2 days after that, I got an email from the CTO of the company, and we had an interesting conversation. Lucky for us, at that time, they upgraded their software. They also realized the software was not the best, so they had some PID type controllers for lane keeping and adaptive cruise control. The version that they had by the time we published the paper was based on MPC, and it was performing much better. But I had an interesting conversation with the people at the company. So we wanted to take this one step further, and we started thinking about, can we do something similar for vision-based controllers? And here's a controller that's trained end-to-end, that takes images and that makes steering decisions. And it's based on a neural network. So we trained the neural network using an MPC type controller. And this is a standard behavior of this neural network controller. And you can run it multiple times from different initial conditions. At each time, it manages to detect this Coca-Cola truck, and it gets around the truck by steering properly. But using our algorithm, you can slightly modify these images. So this is kind of like the adversarial examples in machine learning, but in a dynamic setting. If you slightly modify these images, you can essentially make the same controller fail. And here's an example. It's the same initial condition, but we will perturb the images slightly. And if you perturb the images slightly, then you can make the controller fail. And this algorithm allows you to analyze what these failure cases are, so that you know what type of limitations your controller has. Okay. So this is an overview of formal methods for cyber physical systems. I try to cover all the main techniques here, but there's a big elephant in the room that I didn't talk about, which is the specification. So all of these methods rely on having good specifications. And what I will argue in the remaining part of the talk is that coming up with good specifications is not an easy problem itself either. So going back to the adaptive cruise control problem, in engineering, we spend lots of time talking about mathematical models of systems. For example, in many graduate programs in mechanical engineering, you will have a vehicle dynamics course, an entire course that will teach you how to write down this physics. Or if you're in electrical engineering, you will have a circuits course that will tell you how to write down the physics for an electric circuit. But we don't talk that much about formal specifications. And if you want to use these type of tools, I would argue that specifications are as important as models of physics. So when we started working on this adaptive cruise control problem, the first attempt we had for the specification was the following. If there is no car in front of you, you should go at a set speed given by the user. So this is your regular cruise control specification. And if there's a car in front of you, you should just follow the lead car with some safe distance or safe headway. Would this work? So we synthesized the controller using this specification. The algorithm is correct. It gave us a correct controller. We implemented this controller. And if you put a lead car in front of this car, that is slow initially, then the lead car exceeds the speed limit. Our car was exceeding the speed limit as well because it's just following the lead car. Then if the lead car gets a ticket, you get a ticket as well. Indeed, it didn't work. Then we were like, okay, this is not that easy. We went to this standard documents from ISO and SAE. It was like 2-3 senior PhD students, 2-3 professors studying the standards documents for a week or 10 days, and we wrote down a more complicated specification that did the job. But the question is there an easier way of coming up with specifications? If you are doing this, if you want to use the synthesis type approaches, and if you want to use the synthesis type approaches specifically in robotics domains where these robots will be deployed in small manufacturing settings or in households where the user might want the robot to do something, you cannot expect the user to think for a while to come up with these type of specifications. There should be an easier way. You shouldn't need like 4 or 5 PhDs working on writing the specification for 2 weeks. And that's the motivation for the second part of my talk. And here data will come into play. So so far we were using models, but nowadays many people try to bring in data and learning into picture when you are designing controllers for robotic systems. And you can use data to learn models, or you can use data to learn specifications as well. And I will talk about how to use data to learn specifications. Of course, there are people who want to use data to learn the controller directly as well, if you like model-free approaches. But I typically like having a model and specification because I believe that gives you lots of flexibility and generality. Because if you have the specification, you can maybe use the same specification with a different robot. So you don't need to do the learning again. Or if you have the model and if your specification changes, you can still use your model and design controllers for different specifications. You lose those types of flexibility and you need new data. And test specifications are useful for control design. They are useful for system monitoring. So Ebru has lots of great work on monitoring with specifications. They are useful for anomaly detection. And we want to learn these specifications from small amount of data. So the other thing that I want to emphasize here is small data. So people talk about big data and how to use big data for learning robot controllers. But again, going back to a household task or a small manufacturing plant, small manufacturing business trying to deploy a robot in their assembly line, you cannot expect these people to demonstrate the very niche assembly task to the robot millions of times so that the robot can manage to do the task for them. So it's not cost efficient. They can rather do the task themselves instead of demonstrating it millions of times. So we really need methods that can use small amount of well-created data to figure out these specifications. And if we can do that, we can get some generalization to perform the same task in new environments or maybe different types of robots. If you have an upgrade to your robot software, you can still do the same assembly task. And for that, we will talk a little bit about learning from demonstrations. And we will see a slight modification of learning from demonstrations to handle these two challenges. One is small amount of data. The other one is learning specifications and constraints rather than cost functions. So learning from demonstration is it's a well-studied topic in robotics, and it has the same motivation. Specifying tasks by hand is challenging. And in learning from demonstrations, you typically have some demonstrations of the task, and you learn a policy which completes the task in similar scenarios. Or you learn a reward instead of the policy. And a common approach is inverse optimal control or inverse reinforcement learning. So the optimal control version goes back to Kalman, and IRL version goes back to the PhD thesis of Andrew and G. And in this classical approach, you assume demonstrator solves an unconstrained optimization problem. So the demonstrator tries to minimize a cost function and gives you a trajectory that minimizes this cost function. And you try to infer the cost so that you can solve this problem yourself. And typically what you do is you have a parameterized version of this cost function. You have some feature vectors that you pick, and you try to learn these parameters such that the demonstrations are optimal with respect to this cost function that you learn. And this is applied in interesting domains. Again, this is from Angie's PhD thesis, where you can do interesting backflips with a helicopter using this type of approach. But it also has some limitations. So one of the limitations is that if you have unknown constraints, it's not clear how you can apply inverse optimal control. So one way you can do is you can try to put them with a soft penalty into your cost function and try to learn a cost function that captures both this optimality type things in your objective and also the constraints. But if you have the soft penalty, if it's a safety critical application, at runtime, it's not guaranteed that you will be able to satisfy the constraint. So there's no guarantee you can satisfy the constraint in this case. The other difficulty is that if you have lots of constraints describing your task, it's very hard to get an interpretable cost function, and it's very hard to find the features that will allow you to capture this very complex cost function that describes both optimality and constraint satisfaction. And it's very difficult to scale to multi-stage tasks because it's very hard to write reward functions or cost functions for multi-stage tasks, even if you know the task itself. And I will show how we can avoid these challenges by directly trying to learn the constraints rather than embedding everything into a cost function. Okay, so here is the version of our problem. We assume the demonstrator is solving a constraint control problem. And they are giving us a trajectory, it's a state input trajectory that optimizes this problem. And demonstrator knows everything about this problem. But there are parts that we don't know. For example, we don't know this safe sets that's parameterized by some parameter theta. And this is unknown to us. But there are also some known constraints that we can utilize. Maybe we know the start and end conditions. Maybe we know the dynamics. As I claimed in the first part, for many robotics applications or many vehicles applications, it's easy to come up with a model for your physics, unless you are doing soft robotics, which is hard. So there might be certain constraints that you know, but there are also constraints related to task that you don't know. And our goal is, okay, here's an example. For example, this is a manipulator carrying a heavy object. And there's a bunch of glassware here. And there's a cylindrical region above this glassware that you are trying to avoid, or the demonstrator is trying to avoid, because they don't want to risk this heavy object slipping from their hand and crash the glassware. So these are the type of demonstrations that you see. And there's a cylindrical region, maybe parameterized with by some parameter theta, that you are trying to learn from these demonstrations. And the learner's problem is to find this theta. And once you find this theta, that means you can construct this unsafe region. subject to the fact that these demonstrations that you observe are optimal. So what are the challenges with this problem? So one big challenge if you are a learning person is that we need to distinguish between valid and invalid behavior. Here, valid behavior are those that satisfy the constraints, and invalid behavior are those that violate the constraints. Only from valid examples. I cannot go and tell in many applications the demonstrator to violate the constraint so that I learn what the constraint is. I don't want to crash the glassware just because I want my robot to learn not to crash the glassware. So this is kind of different than typical classification approaches in machine learning, where you will have examples from both classes. Here we have examples from single class. And the other thing that's going to be different from learning is that we have a limited number of examples. How do we overcome these challenges? We will explicitly use demonstrator optimality. Our examples show that demonstrator optimality is a very strong prior and can help you learn these constraints with very few examples. And our key insight is to use Krush-Tucker optimality conditions, because if demonstrations are optimal, they should satisfy, even if they are locally optimal, they should satisfy these optimality conditions. So what are Krush-Tucker optimality conditions? If a demonstration is optimal for a given constraint parameter theta, it should be primally feasible, meaning for each theta there's a corresponding constraint. And if this theta is a valid theta, all the demonstrations that I see should be feasible with respect to this theta. And here, this ellipsoid, if this is the constraint parameterization that I have, is not a valid theta because my second demonstration is violating the constraint. So primal feasibility just tells us what type of ellipsoids or which parameters are feasible for my demonstration to be feasible. So primal feasibility is one thing. The other thing KKT conditions tells you is the stationarity. And this essentially says is that a theta defines the optimal trajectory. A theta makes your demonstrations optimal if you locally perturb these demonstrations. You either violate the constraint or you increase your cost function. And here, this ellipsoid corresponds to a valid parameter, because for this ellipsoid, if I move my demonstrations locally, I either violate the constraint or I increase my cost function. And here, the cost function is simple. It's just like shortest path. And dual feasibility and complementary slackness are just auxiliary conditions that are needed to show stationarity. And if you impose these constraints dramatically reduce the number of valid constraints. The set of theta that are valid reduces dramatically once you impose these constraints. With this, our learner's problem takes this form. We want to find theta subject to KKT conditions being satisfied for all of my demonstrations. And it turns out that for many interesting constraint parameterizations, including unions of boxes, unions of ellipsoids, this problem ends up being a mixed integer linear program, even though your original problem is nonlinear or your original dynamics are nonlinear. There are still some challenges here. And the biggest challenges, all the inverse problems are ill-posed, and this problem is ill-posed as well. And there could be many different theta that can be consistent with this KKT conditions. And here is an example. If I have only one demonstration, all of these ellipsoids are valid, and the theta corresponding to all these ellipsoids will be valid thetas. But you can do something a little stronger. Some of the regions in your state space, no matter what theta you have, all those theta agree on safety or unsafety of these states. So essentially, if you can take the union of all these valid ellipsoids, that the complement of that union has to be safe. And if you can take the intersection of all these ellipsoids, that intersection is guaranteed to be unsafe. And you can also impose this with a very simple check. You can have this additional constraint, and you can have a query point in your state space and impose that query point is unsafe. And if you solve this problem and if this problem ends up being infeasible, that means that query point is essentially safe. And what this enables you is that this is kind of a collision checker in a planner. So if you want to do planning with this type of constraints, you can just use this as a collision checker, and you can plan and you can guarantee that your plan is going to be safe. And we integrated this into RRT type planners where we use this KKT-based approach for collision checking without explicitly constructing the constraints. We can still plan safe trajectories. There are also more sophisticated checks that you can do that takes into account uncertainty and helps you do probabilistic planning. So here are some plans. So this is my original example of carrying a weight over a glassware. We can learn from 3 trajectories in this case, and we can demonstrate new, synthesize new plans from different initial conditions and final conditions. We can have some quadrotors flying around a obstacle course, and we can learn these constraints, and we can plan new trajectories in the same obstacle course that are guaranteed to be safe. And we can also extend these results to multi-stage tasks. And to extend these results to multi-stage tasks, we need to bring a notion of time-varying constraints, and we will use temporal logics to do that. So maybe I won't go into the details that much, but I will show you the results. Essentially, KKT tells us something about continuous continuity, the continuous optimality. We just need a notion of discrete optimality if I have multiple stages in my task. And as I said, we will use LTL to represent these tasks. LTL is linear temporal logic. It has a grammar. And corresponding to this grammar, for every formula, there is a syntax tree, which is a graph. And instead of searching only for parameters, we will search for parameters plus graphs. And that's very easy to incorporate into our original framework, where you still get a mixed integer linear program, but here you are searching both for the graph and underlying propositions that describe the geometry in the workspace. So I won't go into the details, or I will go through the details really quick. But there's one thing here. KKT uses local optimality, and if you have this discrete decision variables in any problem, everything is locally optimal in the discrete sense. For that, we need a notion of discrete optimality, and the main idea here is that if you have globally optimal demonstrations, then you can do something smart, where you can generate trajectories that have lower cost than what you observe. And every trajectory that you generate that has lower cost than what you observe has to violate the specification. And this gives you a way to generate infinitely many invalid trajectories. I told you earlier, we don't have invalid trajectories, but essentially we have a way, if you have globally optimal trajectories, we have a way to generate or tell which trajectories should violate the specification just by looking at the cost function. And with this, you can come up with a counterexample guided loop that searches for these parameters for the discrete part and continuous part. And you can show some theoretical guarantees that in the limits, this is guaranteed to find a constraint specification. So this is kind of the most roboticsy example that I have, I guess. So we implemented this for a multi-stage task. We demonstrated this task in a VR environment. We have 3-4 demonstrations, and the task is grasping a soup can, placing it in a small box, and delivering that to the blue region, then grasping the Cheez-It, placing in the large box, and that's the specification. And in addition to this, the specification includes some rotation constraints, orientation constraints on the gripper, because you don't want to spill when you are carrying the soup. And we can learn these constraints using our approach, and we can implement the same specification in a totally different environment on a physical robot. Here, the positions of the objects are all different, but since the specification is the same, and we are assuming we have a perception module that can recognize objects, you can take this specification and apply it in different contexts. Okay, so wrapping up, what I would say is that both modeling and specifying requirements can be hard, and learning can help for both of them. Optimality is a very strong prior, and if you have curated small amount of data, you can still learn a lot. And we are working on some extensions of this to probabilistic constraints and stochastic systems. And going back, these are some approaches in formal methods for CPS, and they can be applied in robotics. These are useful tools if you want to get trustworthy systems that you can deploy in different safety critical environments. But there are also several challenges in terms of scalability. Learning and trust is still a challenge. You need to make lots of assumptions to say a learning algorithm is correct. If you have humans, if you have human interaction, it's much harder both to specify and model. And there are also, this also includes humans. If you have multiple decision makers that are making sort of selfish decisions, it's hard to scale, hard to analyze, and we don't have good methods for that. And finally, I will finish by acknowledging my students, current and former students. Actually, one of my first students, Yunus, is from METU. He is now an autonomous driving engineer in Sweden. And I want to acknowledge my collaborators as well. And I am happy to take any questions.